if you have a mass which is moving, then this moving object has a momentum. Then the momentum of this object, if you want to find it, it's equal to the mass times the velocity. So in the IB, if you were asked to define the momentum, you can either write the equation and define each physical quantity, or simply say that the momentum is the product of the mass and the velocity. From this equation, it's clear that momentum is a vector quantity because mass is a scalar and velocity is a vector. So the product of a scalar and a vector is a vector. Now the unit of the momentum, simply it's the unit of the mass, which is the kilogram, times the unit of the velocity, which is the meter per second. So this is the unit of the momentum, and it doesn't have any other name. Like, for example, the Newton, it's kilogram meter per second squared. The momentum, it's just like this. Now, something else that I would like to talk about, which is the Newton's second law in terms of the momentum. So we know that from the previous lesson, it's topic 2.2, I guess, we said that the F net, so the net force acting on an object, it's equal to the mass times the acceleration of this object. I can replace A by its definition, which is the rate of change of the velocity. And so this equation can be written as F net equal to m times A, which is delta V over delta T. So this delta V, I can write it as such. So m is equal to V final minus V initial over delta T. And then I can distribute this mass. So I can write it as such. And so I can conclude that this F net, simply it's equal to the final momentum minus the initial momentum, or in another word, F net, it's equal to the change of the momentum over the time interval at which this change occurs. So if you look at this equation here, this is called the Newton's second law in terms of momentum. Now, there's something that I would like to talk about here. Here I have considered the mass to be the constant, but maybe sometimes there are some questions where the mass is variable while the velocity is changing. So in this case, you have to be very careful. Like, for example, in this example. So this example is from Tsoukas' book. You can find it in the worked example. So let's read this. Let's try to figure it out. He's saying that a cart moves in a horizontal line with constant speed v. Rain starts to fall and the cart fills with water at a rate of. So this is the rate at which the mass is changing. You can see every second the mass is changing by sigma. So sigma can take any value. He is asking you, the cart must keep moving at a constant velocity. So in this case, v is constant, m is changing. Determine the force that must be applied on the cart to maintain it moving in this velocity. So this is the same as if you have a supermarket cart and you are pushing it with a force and someone is adding some stuff into this cart. So the mass of the cart is changing, but you have to change the force in such a way that you maintain the same speed. Same idea. So in this case, how to find the force that must be applied, I have to use Newton's second law in terms of the momentum. So I will start by writing F net equal to the change in momentum over the time. But you have to be careful here that this change is only occurring for the mass, which means that the velocity should get out of this change. And I can write the F net as such. So it's V times delta m over delta t. So this is the F net in case the mass is changing. So I can replace this delta m over delta t by sigma, okay, because this is the rate at which the mass is changing, and thus I can know that the force should be V times sigma. Now, if I take the Newton's second law, which is this one that I've been working with, F net equal to delta P over delta T. If I multiply F net by delta T, this is equal to the change in momentum. Now, do you see this physical quantity, the force times delta T? This physical quantity, it has a meaning in physics. It's called the impulse. And it makes sense because impulse, it's like the push. So it's the force that you are applying in a certain time to an object, which will, in some cases, which will cause a change in the momentum. So if you apply a force for a certain time on an object, it will cause a change in the momentum of this object. So I can write that this impulse is equal to the F net times delta T, or it's equal to the change in momentum. Now, I would like to say a note here that this net force, basically, it's the net average force. And why is this? Because sometimes the force is variable. Okay, so like here, for example, in this graph, you can see that the force applied for a certain time, it's variable. So usually we take the average force. Now, how can I find the impulse using a force versus time graph? Simply, it's the area under graph. So the impulse in a force versus time graph, simply it's the area under graph. So for example, if you look at this very first graph, if you are asked to find the impulse in this case, so simply it's the area of this rectangle. So it's the length times the width. So in this case, it's equal to 6 Newton times as 8 minus 2, which is 6. Okay, so the answer is going to be 36. And the unit for the impulse, it's a Newton times second. But also the unit of impulse can be written as the unit of the change in momentum, which is kilogram meter second minus 1. Now, what about this graph? This graph, it doesn't have a definite shape. So how am I going to find the change in momentum, or how am I going to find the impulse in this case? In this case, all what you have to do is to find the area of a small square and to try counting the number of squares. So in another word, we are estimating the impulse. Okay, so you find the area of a small square and you multiply it by the number of total squares under the graph to find the total impulse. Now let's try to solve this example. Also, this example is in your SOCUS book, if you have it. It's the Cambridge book. It has a lot of nice examples and it prepares you well for your exam if you want. So here he's saying a ball of mass 0.2 kilogram moving at 3.6 meter per second. So this is the initial velocity, and this is the mass of the ball. On a horizontal floor, it collides with a vertical wall. The ball rebounds with a speed of, so this is the final speed. The ball was in contact with the wall for 12 milliseconds. Determine the maximum force. So he's asking for the maximum force, not the average force, okay? Which is, so here, this force right here, this is the net average force, okay? He's not asking for this, he's asking for the max. Assume that the force depends on the time according to this figure. So he has given me the relationship, or how is the force varying with respect to time. And he's asking for the maximum force in such a way that the speed has changed from 3.6 to 3.2 in this time. So you can pause the video and try to solve it. After doing this, I tried to look into the answers. So here in this case, we said that the impulse, simply it's the change in the momentum. Okay, but also the impulse, it's the area under graph. Or you can directly say that the change in momentum is the area under graph. So the area under graph, look, the graph looked like a triangle. So it's the base. So this base, it's the 12 milliseconds. So you have, of course, you have to convert it to second. And the height of the triangle, it's what this height right here, this is the F max that he's asking for. So the area under graph, it's F max, the height, times the base, which is the delta t in this case, over 2. Okay, so if I equate this by this one and I have the change in momentum from these physical quantities, I will be able to find the F max. So let's try to do it. So what I'm going to do here is that I'm going to write that F max times delta t. Delta t, it's 12 times 10 to the power of minus 3 over 2. It's equal to the change in momentum, which is the mass times V final minus V initial. So I'm going to consider that V final, which is this one, it's the positive direction of motion. And by the way, it doesn't matter because here we're taking the magnitude, okay? So in this case, the mass, it's equal to 0.2. No need to convert anything here. 3.2 minus of minus, because, for example, if this is the wall and you are going with a certain velocity, so this is the initial velocity, I'm considering this direction to be negative, okay? So the 3.6 is moving to the negative, while in the other hand, once it rebounds, I'm taking the 3.2 to be the positive one, okay? So that's why I'm going to write this as minus 3.6. So it will be equal to 0.2 times 3.2 plus 3.6. Okay, so once you do the math here, so in this case, all what I have to do to find the F max, all what I have to do is to multiply this by 2 and then divide it by 12 times 10 to the power of minus 3. So since I don't have my calculator now, I'm going to skip this for now, but try to do it and find the answer for this one. Okay, so you can find it in your Tsokis book. Okay, now let's go to finding the total momentum. So sometimes you have more than one object moving in a system. Like here, for example, I have this blue block, it's moving in 1 meter per second, and the orange one is moving by 6 meters per second. I'm going to assume that this is a 1 kilogram, okay, and this is a 2 kilograms. So in this case, if you are asked to find the total momentum, simply it's the vector sum. Okay, so it's the vector sum of momentum of each object. Usually we only consider 2 objects, okay? So the P total in this case, if I'm taking this to be the positive, it's going to be the P of the first one, which is M, which is the 1 kilogram, times 1 meter per second. So MV plus MV, so plus 2 times 6. And the answer in this case is going to be 13 kilogram meter per second. On another hand, if I'm going to apply the same rule for this other example, then the P total in this case is going to be the vector sum, which is, so we said that this is 2 kilogram and this is the 1 kilogram. Then it's going to be the momentum of the second one, which is 2 times 8 minus 2 times 1. So I'm adding them, but since this isn't pointing in the negative, so I have to add the negative in this case. So the answer for this one is going to be 16 minus 2, which is 14 kilogram meter per second. So this is how I find the total momentum. Simply, it's the vector sum between the 2 momentums. Now I'm going to talk about collisions. So you have to know that whenever 2 objects collide, like here, for example, Like here, if you look at these two objects, maybe this is at rest, this is moving towards it. So this is what's happening before collision. So if you find the total momentum before collision, if you are taking the two objects, then the total momentum before collision will be equal to the total momentum after collision. Why is this? The reason is because when you take the system of the two objects that are involved in the collision, then this means that the action and the reaction forces, which are the impact forces, they are equal and opposite according to Newton's third law, and thus this relationship, which is F net equal delta P over delta T, is going to be equal to 0, which means that the F net, if I'm taking the correct system of the two objects together, the two objects involved in the collision, then the F net is going to be equal to 0, which means that the change in momentum is going to be equal to 0. Or in another word, I can say that the total momentum before collision, or actually after collision, the final one, so the total momentum after collision minus the P total before collision is going to be equal to 0, which means that these two are going to be equal. So the total after is going to be equal to the P total before, which means that the momentum is going to be conserved. So the momentum is conserved in any type of collision, if we are, of course, taking the correct system, which means that I'm taking the system which includes the forces of impact between the two objects, and in such a way that there's no external force. In another word, for example, if I'm taking the universe as the system, then of course the momentum is always going to be conserved, because always the action and the reaction forces are going to be in the system, which means that the momentum is going to be conserved. So let's talk about the types of collision. So the types of collision are 3. The first one is called the inelastic collision. The second one is called the completely inelastic collision. And the third one is called the elastic collision. Now, what's the difference between these? Before talking about the difference between these, let me say what's the common between these. So the common between these is the momentum is conserved. So in all of these 3 types of collision, the P total before collision is equal to the P total after collision in all of these 3 types of collisions. While on the other hand, the kinetic energy is only conserved in the elastic collision. I'm not talking about the total energy, I'm talking about the kinetic energy. So for example, in the inelastic collision, the kinetic energy, the total kinetic energy before collision is not equal to the total kinetic energy after collision, and the same goes for this situation. So here also, the kinetic energy, the total before and after, are not equal, okay? But here the kinetic energy before, the total before, is equal to the total kinetic energy after collision. Okay, but of course the total energy is conserved in all cases. I'm not talking about the total kinetic. I'm not talking about the total energy. I'm talking about the kinetic energy. So why is this? So the reason here for the kinetic energy not to be conserved is because it's an inelastic collision, which means that part of the kinetic energy here, so here part of energy will go as heat or as sound. Later on you will notice that waves are the transfer of energy, and also it might go as deformation, so in the deformation of the object. While on the other hand, the elastic collision, Of course, this is an ideal situation, but we consider as if the kinetic energy is conserved, which means that no energy will go as a heat, no energy will go as a sound, and no energy will go as deformation. Okay? Whenever you see, like for example, before collision, I have, let's say, two objects approaching one another like this, okay, and afterwards there's sticking happening. So after the collision, they are sticking together. So this means that this type of collision is the completely inelastic, and this comes a lot, okay? Anyway, in order to differentiate between these, let's solve an example. So for example, here in the first image, I have two objects that are approaching one another. So I have an 8 kilogram moving in 10 meters per second toward a 12 kilogram, which is at rest. After that, he's asking me to find the speed after collision of the system of two objects after they stick. So in order to solve this, all what you have to do is to use the conservation of momentum. So for example, I can start with the total momentum before. It's equal to the total momentum after, and this is because I'm taking the two objects that are involved in the collision. So there's no external forces, which means that the total momentum before, it's this mass times this speed, plus, since this one is at rest, so plus 0, okay? So let me write this. So the P total before, I'm going to write it as 8 for the mass, times 10 for the speed, plus 0 for the object at rest, and it's equal to the P total after, which is the sum of two masses, times the common velocity. Okay, so by doing this, this is going to be 80 equal to 20. So the V is going to be equal to 80 over 20, which is equal to 4 meters per second, which means that these two objects that are sticking together will be going in the same speed, which is 4 meters per second. And this is the completely inelastic collision. So this is the inelastic collision. If you want to prove that it's an inelastic collision, try finding the total kinetic energy before collision and try to see if it's equal to the total kinetic energy after collision. You will find that it's not equal, okay? And then, for example, you can find the kinetic energy lost by doing the kinetic energy before minus the kinetic energy after, so you will know how much kinetic energy has been transferred to another type of energy. Now, this collision, let's say he's saying that this is an elastic collision, so the same 8 kilogram object here, the same 8 kilogram is moving with the same previous velocity, and it's hitting a 12 kilogram, which is at rest, but this time they are bouncing away from one another, and he said that this type of collision is elastic, okay? And he's asking for the velocity of this one and the velocity of this one. So this is going to take a bit of time because I need to use the conservation of momentum along with the conservation of kinetic energy. So how am I going to solve this? I'll start by the conservation of momentum. So P total before collision should be equal to the P total after collision. So before collision, I have the same as before, the 8 kilogram hitting the 8 kilogram moving in 10, hitting the at rest object, it's equal to the 8 moving in V1, okay, plus the 12 kilogram moving in V2, okay? Usually they don't give you the direction of motion, so that's why I'm not putting the negative here, okay? So usually they don't give you this arrow, so that's why I'm not putting the negative here. So this is 80 equal to 20 times V2. Excuse me, this is 8V1. So this is 8V1 plus 12V2, and I can't go further with this, so I'm going to put it aside. Of course, you can divide by 4, for example, and so on, but I'm going to keep it like this, and I'm going to call this equation 1. Now, equation 2, I'm going to find it from the conservation of kinetic energy. So in this case, the kinetic energy before collision should be equal to the kinetic energy after collision, because he will tell you that it's elastic collision, which means that half m v squared plus 0, because this one is at rest, is equal to half m1 v1 squared plus half m2, which is the 12 v2 squared. I can remove the halves from all of them, so this is going to be 800 here, equal to, this is going to be 8 v1 squared, and this is going to be 12 v2 squared. So this is the second equation, as you can see. Of course, you can simplify it a bit, but mainly this is the second equation. So what you're going to do now is that you can put one equation in terms of the other. So for example, I can do the following. So I can write this as v1 equal to 80 minus 12 v2 over 8. Okay, and then I can put it in this equation and try finding v2. So in this case, it's going to be 800 equal to 8 v1, but you have to pay attention that it's squared. Okay, over 8 squared, because this is v1 squared, plus 12 v2 squared. So by doing all of the math, I'm going to tell you what's going to be the answer, just one moment. So by doing all of the math using the calculator, you can find that v2 will be equal to 8 meter per second. And of course, you need to substitute this v2 into the v1. So you will end up having that v1 is equal to minus 2 meter per second. So this is how I used the conservation of momentum along with that of the kinetic energy to find the speed after collision for both. So let me just recap everything that we've done till now. What we did is that we said that there are 3 types of collision: the inelastic, the completely inelastic. In those 2 types of collision, only the momentum is conserved while the kinetic energy is not. So usually he tells you what's the type of collision. While on the other hand, if he said that it's elastic, then both are conserved, the momentum and the kinetic energy. So that's how you know which equation you're going to use. I still have 2 more things that I need to mention before the lesson has ended. The first thing that I would like to mention is that in an explosion, so for example, if you have a bomb in an explosion, okay, so in an explosion, the momentum is always conserved, which means that, let's say that this is before the explosion occurs and this is after the explosion occurs. So let's say that this is the bomb, but this bomb is going to be cut into parts, okay? So it's going to be cut into parts and each part will go in a certain direction. Okay, so let's say that this is how the bomb is going to act after collision. So you have to know that the total momentum here before, it was 0, but also after the explosion is going to be 0 as well. And why is this? Because momentum is the vector sum. So if you take the mass of each part of the bomb and you multiply it by its velocity, you will notice that the total momentum is going to be 0. Or in another word, because each part is going to push the other part against by the same and equal force, so this means that the F net is going to be 0, which means that the total momentum is going to be 0 as well. But on the other hand, if we are talking about the kinetic energy, then the kinetic energy before collision, it was 0, but after collision is not going to be 0. Why it's not going to be 0? Because it's going to be the sum of kinetic energy of each part of this bomb. So in a collision, the momentum is conserved, but the kinetic energy is not. And one more last thing, which is finding the momentum or the kinetic energy in terms of the momentum. So if you have to write the kinetic energy in terms of the momentum, you simply have to start with the kinetic energy equation. And if you multiply up and down by the mass, so as if I'm multiplying by 1, so you will end up having this equation as such. So half m squared v squared over m. So this m squared v squared, it's the momentum squared, okay? So I can write that the kinetic energy is equal to the momentum squared over 2m, okay? So I can write the kinetic energy in terms of the momentum. So this is it. This is the whole lesson. These are the main point that you need to know. So first of all, you need to know how to define the momentum, what's the unit of the momentum, and that it's a vector quantity. The second thing that you need to know is that the Newton's second law can be written in terms of the momentum, and this was the derivation. The third thing that you have to know is about the impulse. So the impulse, simply it's the net average force times the time at which the force is acting, and it will cause a change in momentum. So this impulse, also it's a vector quantity, and I can find the impulse by also finding the area under graph. But if the area is not a definite shape, then you have to find the area of a small object, of small square, and multiply it by the number of squares. The last thing that you have to know is that in the different type of collision, in any type of collision, if there's no external force, then the total momentum is going to be conserved, but the kinetic energy, it depends on the type of collision. If it's elastic, then it's conserved. And that's it for today. See you in another video.